Hello teacher, today I would like to present the working principle and the schematic design of my project, a relay-based bidirectional DC motor control circuit. The main objective of this circuit is to control the rotation direction, clockwise and counterclockwise, of a 12 volts DC motor using two independent push buttons to ensure safety and isolate the control logic from the high power load. I will implement an H-bridge configuration. And I would like to explain the component selection for this project. Batteries, dual source, a 9-volt battery for a low power control logic, and a 12-volt battery for the high power DC motor. Voltage regulator steps down and stabilizes the 9-volt input to a constant 5-volt DC to safely power the logic components. Push button switch acts as a manual user input. Pressing it routes 5 volts to the transistor base to trigger the motor. NPN transistor acts as an electronic switch. It amplifies the weak 5-volt logic signal to safely drive the high current relay coil. 9-volt relay form and H-bridge configuration to change voltage polarity and control motor direction while isolating the 5-volt logic from the 12-volt motor supply, and diode placed across the relay coil as flyback diode. It dissipates inductive voltage peaks, protecting the transistor from damage. DC motor, the main actuator, converts electrical energy into mechanical rotation reversing direction based on which relay is active. LEDs, visual status indicators. Green LED lights up forward rotation, red LEDs up for reverse. Resistors limit current to prevent damage. 1 kilo ohm protects the transistor base. 120 ohm protects the LEDs. Power supply section. The circuit begins with battery 1, a 9-volt DC battery, which is the main power source for the entire control circuit. The positive terminal of battery 1 connects directly to pin 1 of a linear voltage regulator. The purpose of using this regulator here is to protect the sensitive control components from voltage fluctuations that can occur from the battery. Even if the battery voltage drops slightly over time, this linear voltage regulator ensures a constant 5-volt output as long as input stays above 7 volt. This is a fixed positive voltage regulator. Pin 1 receives raw 9-volt input. Pin 2 connected to common ground. Pin 3 outputs a clean, stable 5-volt regulated voltage. Next is the power on indicator. As soon as the circuit is powered, 5 volts flows through a 120 ohm resistor to light up the green LED. This gives immediate visual feedback that the system is on and the regulator is working. The resistor limits the current to a safe certain 0.6 milliamps to prevent the LED from burning out. Now let's move on to the core switching and control stage of our circuit, which consists of the transistor, relays and flyback diodes. First, we use two NPN transistors labeled Q1 and Q2. It is important to note that they operate strictly as electronic switches, not amplifiers. When a microcontroller or button sends a high signal to the transistor's base, it enters saturation mode. This closes the circuit, allowing current to flow from the 9-volt supply through the relay coil and down to ground. When the signal drops too low, the transistor cuts off and opens the circuit. Next, we have the 9-volt electromagnetic relays. These components are essential. because they provide complete electrical isolation between our low power control logic and the high power motor circuit. When the transistor activates the current energizes the relay coil, physically moving the internal contacts from normally closed to normally open. By using two relays together, we form an H-bridge configuration to change the voltage polarity and control the motor's direction. Finally, we integrated flyback diodes connected in reverse bias across each relay coil. This is critical protection mechanism based on Lenz's law. When a transistor suddenly turns off, the magnetic field inside the relay coil collapses rapidly, generating a massive reverse voltage spike. Without these diodes, this spike could easily destroy our transistor. The flyback diodes safely clamp and dissipate the energy, ensuring the long-term reliability of our system. Now let's talk about the motor load section. Here our DC motor is powered by a completely separate 12-volt battery. This isolation is an intentional and critical design choice. DC motors draw massive current surges, especially when they first start up or change direction. If the motor and the delicate control logic shared the same power source, these current spikes would cause severe voltage drops, making the entire system unstable. Using battery to dedicate entirely to the motor keeps our control circuit completely stable. The motor itself is wired through the contacts of relay 1 and relay 2 in a mechanical H-bridge configuration. When relay 1 activates, current flows through the motor in one direction, spinning the shaft clockwise. Conversely, when relay 2 activates, the current reverses, causing the motor to rotate counter-clockwise. This gives us full control over the motor's direction. Real-world applications. First, the circuit is exactly how power window and sunroofs work in modern cars. When you press the window switch up or down, it triggers relay 1 or relay 2 to reverse the motor's direction. The regulator stabilizes the fluctuating car battery voltage, while the relay isolation ensures the dashboard switches only car deny safe currents, leaving the high power to the motor stage. The second example is automatic gates, garage doors. This is core system behind automatic garage doors and gates. A remote control sends a signal to the transistor to activate the relays, opening or closing the heavy gate using the high turbo 12 volts motor. Limit switches can be easily added to stop the motor at the right time, and our flyback diodes protect the control electronics from the heavy gate motor spikes. We reached the end of this circuit analysis. I hope this journey through every component, every connection, and every real-world application has given us not just knowledge, but a new way of seeing the world around us. The science of today is the technology of tomorrow. Edward Teller.